Hello, welcome to the second lecture of Sustainable Architecture and Energy module. My name is Katarina Luketina and I will talk about sustainable architecture and energy management in general. So what is sustainable architecture? The diagram on the left gives us a hint of what sustainable architecture is all about. It's a very broad topic. Some parts like energy, waste and water management or renewable energy resources will be explained in separate lectures. In this lecture I will focus mainly on good examples of sustainable architecture and energy management. So the first example shown on the right picture is Anna Heringer's and Aike Rozvak's Smeti or handmade school in Bangladesh. Sustainable architecture, explained according to Wikipedia, is architecture that seeks to minimize negative environmental but also social, ecological and economical impacts of the building. It concerns about development of space and ecosystems at large. It also concerns that our actions and decisions today do not inhibit the opportunities of future generations. Energy efficiency over the entire life cycle of a building is the most important goal of sustainable architecture. On the pictures below we can see Tin Tegenstue. This is a Norwegian architecture office and they build these buildings in Thailand. Let's talk some more about energy efficiency in architecture. As anything else, every building has ecological or carbon footprint. To learn more about carbon footprint, watch the video embedded in the page below. This is because we need energy to produce building material, plan, build, maintain and eventually dismantle or demolish the building. We shouldn't forget that we have to appropriately dispose once used building materials. This is what we call life cycle of a building and we will talk about it later on more. Sustainable architecture comprises more than just ecological or carbon footprint. Parts of this term is also something called human development, which includes life expectancy, literacy, wealth and or welfare. In the picture on the left side, we can see a typical family from Mali on the roof of their house with all of their belongings. More about this you can learn on the link below. And you can also see more examples of different families and a carbon footprint. And when you talk about energy efficiency in building, the story is not that simple because of all this already said. However, for the sake of this lecture, let's say that we can divide the overall energy consumption in building into embodied energy and operational energy as consumed energy, minus gained energy, and this is energy gained with passive or active systems which are part of the building. We can see this balance more elaborated in the diagram on the right side. Here we cannot see embodied energy or energy used to build and produce building material. However, when we start thinking about building or designing a new building, we should ask ourselves some important questions, and the first one should be whether it is necessary to build at all, because greenest building is the one that is not built. It is usually better to reconstruct or convert an existing building. These are the pictures of one architect, his name is Ricardo Bofill, home and office which used to be a cement factory. It is located in Spain. We should always firstly think about environmental impact of a building, especially moderation in the use of unbuilt natural space or ground. Furthermore, some important terminology concerning sustainable conversions are adaptive reuse. This is a process of reusing an old site or building for a purpose other than which it was built or designed for. Here we must be aware of local building regulations and heritage preservation regulations if those exist for a particular building. And when designing anew, we should always design for flexibility and desirability to maximize the building life. All of these pictures are old structures reused for a new function from different parts of Europe. The picture on the left is Tate Modern Gallery in London, which with its latest annex designed by Swiss architects Herzog de Meuron. Second principle of sustainable design is that if there is a need to build, it is important to build the smallest area possible, like tiny houses, non-permanent or easily dismantleable structures. Here in these pictures we can see some examples of this. First, on the upper left above is Makoko Floating School in Nigeria by Kunle Adeyemi. He's an architect of this school. The school is floating on the sea. Then on the right side above is Tien Tegenstues orphanage in Thailand. These are very small units. Then on the left picture below we can see one architect's thesis project, and this is actually a renovation of an old school bus which became his home. And the bottom right picture is a typical tiny house, because this movement is becoming even more and more popular lately. Another important issue concerning sustainable design is avoiding building sprawls, and we should always, instead of building sprawls, focus on building sustainable urban or rural settlements like eco-districts or eco-villages. Here in this picture we have the example of first UK's eco-district. It is called BZ. It is located near London, and BZ actually means Beddington Zero Energy Development. You can learn more about it at these links. There are of course many other examples of this kind of eco-districts or eco-villages, especially in Europe nowadays. One similar example is Vauban in Germany near Freiburg, and there are of course many others. I encourage you to learn more about this. Of course, we should always design according to users' lifestyle, financial, social and other preferences. Sometimes sustainable design interferes with lifestyle of inhabitants, because our habits affect sustainability. What we eat, where we work, what kind of transportation we use, how we spend our leisure time, what kind of comfort we expect, all of these affect energy and resource consumption. This is why education of inhabitants and sometimes change of their habits is part of sustainable use of the building, and it is very important. The pictures below show region villages by Danish architectural collaborative called Effect. First of these communities will be built this year in Netherlands. Basic principles of design are energy positive homes, doorstep high-yield organic food production. You can see in the picture that every dwelling unit has a garden for food production. Then a mixed renewable energy and storage, water and waste recycling, empowerment of local communities, and you should learn more about this at this link here. Another important way of reducing energy demands of the building is by using passive solar design. This basically means that we should design according to local conditions, climate, topography, vegetation, orientation, and surrounding buildings. General principle of passive solar design is the use of sunlight without active mechanical systems. These buildings are designed to let the heat into the building during the winter months and block out the sun during hot summer days. Ideal site location and house plan is maximally exposed to the sun from 9 a.m. to 3 p.m. in winter time. This way heating energy can be reduced from 25 even to 75%. These principles are well known from ancient times, and they say that even Socrates' house was built this way. In these pictures and diagrams you can see basic schemes in which way to imply this kind of design. There are different types of passive solar systems. First I will talk about direct gain. This is a type of passive solar design system where we have living space as a kind of a solar collector. Especially most frequently used rooms in house are suitable for this. The black and white pictures on the left side of the slide show us this principle alive. These are the plan and interior space of Frank Lloyd Wright's house in United States. It's actually a torus-shaped building oriented towards the south with stone wall acting as thermal mass. Then we distinguish indirect gain as a passive solar design system. Here we have attached greenhouse or trombe wall that act as a solar collector. You can see the pictures on the right side of this slide regarding this indirect gain. Trombe wall is a wall built on the south side of building, exposed to the winter sun and shaded from summer sun. It's important that this wall is made of high thermal mass material, painted in dark colors, and separated by a thin layer of air from glass facade in front. In this way, trombe wall uses basic greenhouse principle that heat from sun passes through glass and warms thermal mass, which then releases the heat to the interior during colder winter nighttime. We can see this elaborated on the pictures on the right side. The lower right picture is actually Mr. Trombe's house. This is the first use of Trombe's wall. And you can learn more about passive solar design system in Edward Mazria's book called Passive Solar Energy Book. You can see this book in the picture in the middle of this slide. Important elements of passive solar design systems are thermal mass. This can be any kind of masonry work like brick or stone, concrete, but also some other materials like rammed earth, adobe wall, or even water. We can see the picture of this on the slides on the right side. Above we have Steve Byers' house in USA, which has some kind of trombe wall with water barrels painted in black, in front of which is south glazing. This house also has these big shutters, which can act as a reflecting surface to enhance solar gains when opened, or they can prevent excessive heat losses or gains when closed. Then we have solar windows. These are any kind of south-facing windows. For this reason, house plans should be elongated in east-west direction as to have maximum south-facing windows. And of course we have solar shading. This is a control system that prevents excessive summer sun to enter the building. This can be any kind of external shading devices like shutters, blinds, roof overhangs. Even the deciduous trees in front of south facade can act like solar shading. We can see this principle alive on the pictures on the left side. The bottom left picture is passive house made of plaster straw bale on Ezerhof estate by Swiss architect Werner Schmidt. On the right picture below we can see swimming pool as thermal mass in attached sun space. We can use passive solar design principles to cool the building too. This can be in the most simple way cross ventilation in more temperate climates. This is quite suitable, but in more hot climates we need a double roof like in this health center in Burkina Faso by Kere architecture, or even more complex systems like different kinds of solar chimneys like this French school in Syria. These systems can become even more elaborated like wind catchers in this vernacular architecture in Hyderabad Sindh in Pakistan, or wind towers like in this picture from Yazd in Iran. Here we have these wind towers, which are part of Kanat systems. That is actually part of water supply systems that cool the building down. I encourage you to find out more about this and to find out more about passive solar design components on this link below. When designing according to local climate and natural situation, it is important what kind of materials we use. I would start this part of lecture with the term embodied energy. This is sum of all energies required to produce any goods or services or applied to building. It means it is energy consumed by all of the processes associated with production of a building, from the mining and processing of natural resources to manufacturing, transport and product delivery. It can be measured for every material, and it is measured in megajoules of energy needed to make a kilogram of a product. Generally speaking, the lowest embodied energy is for locally produced natural or minimally processed materials. To reduce impact of embodied energy, we should design a long life, durable and adaptable buildings. Ratio of embodied energy to operational energy is estimated 30 to 70%. Operational energy is energy consumed throughout the lifetime of a building for heating, cooling, hot water production, etc. Life cycle assessment is a more complex technique to assess environmental impacts associated with all the stages of product's life from cradle to grave. This is actually kind of an open cycle, and it examines the total environmental impact of a material or product through every step of its life, from obtaining raw material, through mining or logging, all the way through manufacture, transport to a store and using it in home, to disposal or recycling. We distinguish this in contrast to cradle design. This is actually a regenerative or biomimetic design. It models human industry on nature's processes, viewing materials as nutrients circulating in healthy, safe metabolism. This is a closed cycle design. Important terms here are in this exact order: reduce, reuse, repair, recycle. But we must be aware that recycling usually spends quite a lot of energy and is actually downcycling. That means that it converts waste material into materials of lesser quality and reduced functionality. We distinguish this in contrast to upcycling, and upcycling is actually creative reuse, which is a process of transforming waste materials, useless or unwanted products, into new materials or products of better quality or of better environmental value. We can see this principle alive in these pictures on the left side. These are actually rural studios designs. The picture above is carpet or Lucy's house, where we have old thick layers of carpet from carpet factory leftovers used as facade wall. Then we have on the bottom left picture Yancey Chapel, where they used old car tires filled with earth as sustaining wall and plastered with earth. And on the bottom right picture we have Windshield Chapel, where they used old cars windshields to make this glass facade. Besides compromising the environment, some materials used in building can be harmful to our health too. Here we can distinguish biological agents, bacteria, fungi, molds and spores. Then chemical agents, different chemical compounds, heavy metals, fibers and particles. And physical agents. These are ion imbalances, electromagnetic fields, radio frequency radiation, etc. Sick building causes are frequently pinned down to flaws in the heating, ventilation and air conditioning systems. Up to 30% of new and remodeled buildings worldwide may be subject of complaints related to poor indoor air quality. All this can be prevented with the use of natural and minimally processed building materials, or with increased ventilation rates, proper and frequent maintenance of heating, ventilation, air conditioning systems, then replacement of water or mold stained ceiling tiles and carpeting, and of course with indoor planting of toxin absorbing plants, as in this picture above. When we talk about materials for exterior building envelope, except materials for finishing facade and roofing, we distinguish load-bearing structure materials of high compressive or tensile strength. These are materials of high specific gravity usually. These are concrete, steel, and brick, which are higher on embodied energy, in contrast to stone, wood, bamboo, adobe, rammed earth, which are usually materials of lower embodied energy or CO2 emissions. Then we have thermal insulation materials. These are usually lightweight materials of no compressive and tensile strength. These are polystyrene like styrofoam, then polyurethane, glass, and mineral wool, which are materials high on embodied energy. Then we have straw bale, sheep wool, cork, cellulose, and hemp, which are lower on embodied energy and CO2 emissions. And materials for both of these functions, which are different kinds of lightweight concrete, hempcrete, and papercrete, etc. We should always try to use materials of lower embodied energy and easily reusable and recyclable materials. But sometimes materials of higher embodied energy significantly lower operational energy, as in case of thicker thermal insulation. 3 rules of sustainable building is insulation, insulation, and insulation. This is of course a joke, but super insulation as a design approach was an ancestor of passive house design we know today. On the pictures below we can see how different materials are suitable for different climates. On the left picture we can see hostels in China near Shanghai made of stone, rammed earth, and bamboo by architect Anna Heringer, where she employed local craftsmen and their skills for this project. And on the right picture we can see a house in completely different climate near Ontario in Canada, which is made of straw bales with passive house standard. And all of this brings us to next important subject. Energy consumption in building. You could hear more about this in the previous lecture, but here it is important to know that this has to be measured and calculated. Buildings get certified according to this calculated energy consumption in different categories, which are labeled with letters from G to A+. Pictures above are of so-called S-house in Austria, which is one of the first passive houses built with straw. This means it has A+ standard in terms of energy consumption, and it is made entirely of natural building materials. In this case, it is a timber construction with straw bale thermal insulation, plastered with clay, and with timber cladding facade. Again, here we have passive solar principle applied, because you can see in this left picture, which is a picture of south facade with very opened glass windows, and the right picture is the picture of north facade, which is quite close and still. More important terms when we talk about energy consumption in building are lower energy house, or so-called 3-liter house. This corresponds to a house that uses approximately 3-liter fuel oil per square meter living space a year. That is less than 30 kilowatt hours per square meter a year, and it is certified with letter B. Then we have passive house, or 1-liter house, which uses less than 1.5 liter of oil to heat, and it is certified with letter A. And here we have example of another passive house, or 1-liter house, which is also straw bale house. This time it's prefabricated timber construction filled with pressed straw. Then we have zero net energy house or zero energy building. That means that total amount of energy used by the building on an annual basis is roughly equal to the amount of renewable energy created on the site. Built example here is from Australia, and it is a rammed earth house. Then we have plus energy house, which produces more energy from renewable energy resources over the course of a year than it imports from external resources. This house is from Denmark, and it has huge south-facing slope windows with a system that can fill the windows with polystyrene balls in wintertime to prevent excessive loss of heat, or in the summertime to prevent excessive heat gain. Then we have an energy autarkic or autonomic house. This means that the building is independent of third parties concerning energy consumption for living, and these kind of houses are self-sufficient regarding energy consumption. They are also called off-grid houses. And here we have on this picture Monte Rosa cabin, which is a high alpine building, which is presenting also a high degree of energy autarky of over 90%. Passive house standard is one of the standards to achieve very low energy consumption for maintaining comfortable indoor climate. Here are basic principles of this kind of design. It employs continuous insulation through its entire envelope without any thermal bridging. You could hear more about thermal bridges in a previous lecture. The building envelope is extremely airtight, preventing infiltration of outside air and loss of conditioned air. Then it employs high-performance windows and doors. Typically so-called passive windows are triple paned with low E glazing filled with argon or krypton to prevent heat transfer to outside space. It also uses a form of balanced heat and moisture recovery ventilation and uses a minimal space conditioning system. At least 75% of heat from the exhaust air is transferred to fresh air by means of heat exchanger. This usually means using other types of renewable energy sources. And of course, we have solar again, which exploits the sun's energy for heating purposes and to minimize it in cooling seasons. You can find out more at this link here, which is actually official Passive House webpage. Similar to passive solar technologies, green or living roofs and walls have been known from ancient times. A sod roof or turf roof is a traditional Scandinavian type of green roof covered with sod on top of several layers of birch bark on sloping wooden roof boards. Until the late 19th century, it was the most common roof on rural log houses in large parts of Scandinavia. The top left picture is from Iceland, actually. Advantages and environmental benefits of green roofs are: they reduce heating and especially cooling needs of a building. Then they reduce urban heat island effect. Top right picture and the one just below show this. Then they reduce stormwater runoff. They also filter the water before it goes into sewage system. They also filter pollutants and carbon dioxide from air. We can distinguish intensive and extensive green roofs. They vary on depth or earth layer, height and mass of plants planted, and the need for maintenance. Extensive roofs are more common. They have plants like sedum species or mosses planted. The bottom right picture is green roof on Renzo Piano's Academy of Sciences in California, and the bottom left picture is Patrick Blanc's vertical garden on Jean Nouvel's Musée de Quai Branly in Paris. Here are some more examples of intelligent energy-saving methods like earthships. Earthships are a type of passive solar houses made of both natural and upcycled materials such as earth-packed tires. Airships are designed and marketed by Michael Reynolds from United States. This kind of design addresses 6 principles of human needs. Thermal solar heat and first thermal solar heating and cooling, then solar and wind electricity, then they contain sewage water treatment, then they are built with natural and recycled materials. They have water harvesting and food production. Top right picture is house designed by architects C. Ark and Christian Miller in Val, Switzerland. This building uses the same basic idea as airships, and that is constant soil temperature throughout the year to reduce heating and cooling demands of the building. Bottom strip of pictures show a reconstruction project of social housing high-rise buildings by French architects Lacaton Vassal. We can see here before and after situation of the same spaces or building facade. As we are coming to an end of this lecture, I would like to mention the problem of waste. We will talk more about waste management in another lecture, but here I wanted to emphasize the importance of avoiding construction waste, especially at the design phase. Buildings should be designed so that after its lifetime, every building component can be reused or at least recycled. In this way, we can avoid waste as such, or at least we can avoid energy consumption to properly dispose or recycle waste. This is my last slide. Thank you for your attention. Please check out the links below for more information, and goodbye.